about things, believe it, I will always be there. So
in the last video for this section, I just want to do one example of a definite integral of the kind you might see on an exam. Let's look at the integral from 6 to 6 times the square root of 2 of x over the square root of x squared minus 36. So let me say right at the beginning, we'll do this two ways. The first way is I see a square root of x squared minus 36, and that really makes me want to do the substitution x equals 6 secant theta. So that dx is 6 secant theta tan theta d theta. And now the square root of x squared minus 36 is equal to 6 times the square root of secant squared theta minus 1, which is 6 tan theta. Because secant squared theta minus 1 is tan squared theta. So the integral we started with, 6 to 6 times the square root of 2 of x over square root x squared minus 36 dx is equal to the integral from somewhere to somewhere. We'll have to adjust endpoints. But first, let's just see what function we're going to integrate. We get a 6 secant theta from the x divided by 6 tan theta times secant theta tan theta d theta. This tan theta cancels with this tan theta. This 6 cancels with this 6. Oh, we have another 6 here. So what we get is 6 times the integral of secant squared theta d theta, which we know is 6 times tan theta. But now I realize that I've been forgetting all of these endpoints. So the question when you adjust the endpoints is, what is theta when x equals 6? Same question, what is theta when x equals 6 root 2? Well, if 6 equals 6 secant theta, then secant theta equals 1. So 1 over cosine theta equals 1. So theta equals 0 is our new endpoint. Same thing, if 6 square root of 2 equals 6 secant theta, then square root of 2 equals secant theta. This is a value you should know, because here we want cosine theta equals square root of 2. 1 over cosine theta equals square root of 2, which means that cosine theta equals 1 over square root of 2, or you could rewrite this as square root of 2 over 2. So theta equals pi over 4. All right, so we write in these endpoints, pi over 4, 0, and applying FTC2, now what we get is just 6 times tangent of pi over 4 minus 6 times tangent of 0. Tangent of pi over 4 is 1, and tangent of 0 is 0. So what do we get for this integral? 6. So I'll pause and erase, and then I'll show you a different way to do this same integral. Now we'll do this same integral by a different method, and this second method is going to be easier. I see a square root of x squared minus 36 in the denominator. We're taking the square root, some outer function, of some inner function x squared minus 36. We have an x dx in the numerator. Well, if we set u equal to x squared minus 36, then du is 2x dx, which is almost what we have in the numerator. So instead of having a du, we have a 1/2 du. So that means that the integral that we started with, x over square root x squared minus 36 dx is equal to the integral from somewhere to somewhere that will adjust in a second of 1/2 du over square root of u. So what are the new endpoints? Well, what is u when x equals 6? 6 squared minus 36 is 0. And what is u when x equals 6 times the square root of 2? We square this, we get 6 squared times 2, which is 72 minus 36 is 36. So what do we need to know? Let me just rewrite this. 1/2 integral 0, 36. U to the minus 1/2 du. And an antiderivative of u to the 1/2 is 2 times u to the 1/2. So we get 1/2 times 2u to the 1/2, because when you take a derivative, the 1/2 and the 2 cancel. 0, 36. This just is square root of 36 minus square root of 0, which is equal to 6, which is the same thing we saw before when we did this problem by trig sub. So what happened in this problem? One thing I wanted to show was that definite integrals with trig subs are quite a bit easier than indefinite integrals with trig subs. But I still fell into a kind of trap here, where first I saw square root of x squared minus 36 and thought immediately, aha, I want to do a trig sub with x equals 6 secant theta, when actually it's a lot easier to first just do a u substitution. So I know you want to be fast when solving integrals on the exam, so you want to practice lots of different problems, and you want to kind of know what to do without having to stop and really think for a long time. But if you take an extra second with a problem like this to think, is there something easier that I can do than going directly to a trig sub? It will save you time in the end.